Welcome to The Explainer. So today, we're diving into this really fascinating idea from our source material. What if cooperation isn't just, a nice thing organisms do? What if it's actually a fundamental, predictable rule of the universe? Something as inevitable as the laws of physics themselves? It all kicks off with this puzzle that even Darwin himself really struggled with. If life is all about survival of the fittest, this constant, brutal competition, then why, when we look around, is the natural world just overflowing with partnership, with alliances, with all kinds of cooperation? And this isn't some one-off rare thing. I mean, take the Namibian savannah. You've got hornbills and mongooses actively working together, watching each other's backs for predators. And this kind of mutual support, it's everywhere you look, from the smallest microbes to the most complex animal societies. Cooperation is a seriously powerful force out there. So, to crack this puzzle, today's source material says we need to kind of reverse engineer these relationships. By using this powerful mathematical lens, it's called the Modified Energetic Lotka Volterra framework. It actually uncovers what it calls a blueprint for harmony. All right, so to really get this blueprint, we've got to start at the foundation. What are the absolute non-negotiable rules of the game for any system where things interact? Well, in math and logic, they call these foundational rules axioms. Think of them as the self-evident truths, the absolute bedrock that everything else is built on. You don't prove them, they're just the starting points you have to accept before you can figure anything else out. Now, this brings up a really critical difference we have to get our heads around. On one side, you've got the axioms. These are the basic rules of the game. And on the other, you've got the principles, which are the consequences that just naturally happen when you play by those rules. So this whole blueprint is built on 8 of these core axioms. For instance, you have energetic accounting, which just means every interaction has a cost and a benefit. Then there's local emergence, which says that order just kind of bubbles up from the bottom, without some master planner calling the shots. And what's cool is, these rules are so basic, they could apply to anything that interacts, not just animals. And here's something that's absolutely essential to get. These axioms are totally neutral. They don't care about good or bad or right or wrong. They're just describing the basic physics of how things interact. They tell you what happens, not what should happen. So, what happens when you let a system run based only on those simple, neutral rules? What are the consequences of just playing the game? You might expect total chaos, right? But that's not what the math shows at all. When you start with these 8 simple axioms and apply some serious math, you don't get randomness. Instead, these predictable patterns of cooperation and harmony just emerge as the only logical conclusion. And these results, well, these are the principles. And unlike the axioms, they aren't assumptions we start with. They're powerful truths that are the direct, unavoidable consequence of playing by the rules. So you got principles like interaction cost minimization, which basically says systems are always pushed to find the easiest, most energy-efficient way to get things done. And then there's thermodynamic inevitability, which shows that because cooperation is so darn efficient, it often ends up being the most stable, preferred state for a system to settle into. And this quote just nails the core idea perfectly. Cooperation isn't some high-minded ethical choice or a philosophical goal. In this view, it's a consequence of thermodynamics, a pattern that just pops out from the fundamental laws of energy and efficiency. Okay, this is a beautiful theory, it's elegant, it's powerful, but here's the billion-dollar question, right? Does this mathematical blueprint actually match what we see happening in the real world? And amazingly, the answer is a resounding yes. When you test the model's predictions against real-world data from ecosystems, this blueprint explains over 92% of what's going on. That's not just a good fit, that's an unbelievably strong fit. But wait, it gets even better. The math actually predicts that under normal conditions, a stable cooperative state isn't just a possibility, it's going to be the default outcome about 78% of the time. It turns out competition is actually the exception, not the rule. So we're not just talking about a good fit or some interesting little correlation here. The source argues this is a stunning confirmation that these underlying mathematical rules, the axioms and the principles, are profoundly accurate at describing how the world really truly works. So, okay, a mathematical model of ecosystems. That's cool, but why should we really care? Well, because these rules, as it turns out, aren't just for biology class. Remember how those axioms were defined? They weren't specifically about animals or plants. They were written to apply to any system of interacting adaptive entities.
basically any system where the parts can adapt and interact with each other over time. And that means the exact same principles that build harmony in a forest can help us understand cooperation in our economies, in our social systems, and even in our technology, like AI networks. The math is universal.
So what does this all boil down to? We're looking at more than just a description of nature. The axioms are the foundation, the principles are the building itself, and when you put them together, you get a functional blueprint for how stable, harmonious systems get built at any scale.
And this leaves us with a final, really provocative thought. If cooperation is already baked into the fundamental laws of how systems work, then maybe our job isn't to try and force it to happen. Maybe our real job is just to understand this blueprint, create the right conditions, and then just step back and let the laws of physics do the rest.